All right, hello everybody. So this is our pre-recorded review session for EGME 333 for fluid mechanics. So this is the review session for midterm 1. And so just like I promised you guys, I looked at the poll on Canvas, and from that poll I found that these 3 topics were the most requested. So what I'm going to do is I'm going to run through these topics over the next hour or so. And I'll definitely get through the first 2, and then if I have time at the end, then I'll cover Bernoulli really quick. But I really want to make sure that I cover hydrostatic forces on surfaces and manometry, because these were the 2 that were most requested. Okay. All right, so let's jump right in. All right, so the first topic that we want to go over is hydrostatic forces on surfaces. And so the whole idea with this unit, so this was, one of our topics in our big unit on hydrostatics, is the fact that, because whenever you have a static fluid, something like this, okay, and we know from before that as you go deeper into the static fluid, the fact that you have, more and more fluid above you, it increases the pressure force. Okay? And so remember our equation for this, where if we had this 0.1 and this 0.2, right? If we compared the pressures in between these 2 points, okay, and we say that the height in between these guys is h. Okay? And so the difference in pressure between these guys will be minus, their height difference, h, times rho, which is the density of the fluid, times gravity. Okay? Right? And so as you go deeper, then the pressure is going to increase. And what we know about pressure from its dimensions is that pressure is nothing more than just a force divided by area. Okay. And so because of this, whenever we submerge a solid surface into a fluid, a static fluid, then those surfaces are going to experience a force. Okay. And so the whole idea with this unit was to basically, you can kind of think of it as almost like an extension of your typical statics class or strength materials, is to see, if we submerge surfaces into a fluid, what are the magnitudes of the forces and what are the locations of the forces. Okay. And this is used in all manner of kinds of, if you're designing like a basin that's going to hold a large body of water, and it's used a lot in boat design too, or any vessel that has to go underwater, because all of these things have to be able to withstand these pressure forces. Okay? And so the main things that we want to search for, or that we want to solve for in these cases, are, first of all, what's the magnitude of the pressure force? Okay. And so basically, what's the measurement of the force in like newtons or kilonewtons or pounds of the force, right? So that's obviously going to be important to know. And then the second part is the location. Okay. And so anytime you come across a problem which is asking you to solve for the hydrostatic force on a surface, either by computing a moment or, I think, you guys are starting to get the hang of what these questions look like. The first thing that you should always do is compute, what's the magnitude of this force and what's the location of this force. Okay? And computing these things can be tricky because of the fact that pressure is not constant, as we go down in the fluid. So remember, as we go down in the fluid, pressure is going to increase. So as you go deeper, the pressure and the forces are going to increase. Okay. And so this is complicated because sometimes you might have surfaces that are, not completely flat. They might be inclined, right? And so if we draw like a simple, let's say that we have an inclined surface like this, over here. And then what's going to happen here is that the pressure, you can kind of think of it as a distributed force across the surface, but this distributed force will be higher on the lower parts of the surface compared to the higher parts. Okay. Okay. And so the whole idea with this is that, even though we know that the pressure distributes the force over the entire surface, this is usually not that useful for calculations, or you can, but it's it's usually difficult. And so what we want to do, so that we can use it together with free body diagrams and stuff like that, is we want to replace this pressure force with replace this distributed force with a single force vector. And we often call this force vector the resultant force. So instead of like a distributed force you see up there, we have just one force vector like this. Okay. And so with that single force vector, we can we can use this to solve for the static equilibrium, or even just the sum of the moments have to all equal 0 as well. Okay. Okay. And just like we said on the previous slide, what's going to be interesting in this is what's the magnitude of this pressure force. And also, where's the location? So the location could be somewhere like this. Okay. And usually we denote location with the y. Okay. Okay. So usually, I think the most difficult things about these types of hydrostatic force problems is imagining the geometry. So there's oftentimes, especially if you have an inclined surface, you have to deal a little bit with trigonometry. You also have to have a little bit of imagination too, because oftentimes when we view these surfaces, we're viewing just the side profile of it. But you have to kind of, in your mind, just kind of turn the surface like this and tell yourself that there's also a full surface over there. Okay. Okay, so what formulas do we need to use for this? So there's two main formulas. Okay. Just like we said before. Right? So I won't go through the whole derivation again. So for the full derivation, you can definitely check out the recorded lecture from our fluid statics unit. Okay. And so the first thing that we want to compute is the magnitude. Okay. Okay. So usually, this is just given the symbol just FR. But if you want to be, totally precise and say that this is the magnitude of a vector, you can add the two kind of vertical lines up there. Okay. As the formula that we had from class was the following. Okay. And so the formula that we had from the class was that the magnitude of the force will be gamma, where this, remember this guy is the specific weight. Okay. It's the weight of the fluid per unit volume. Okay. This HC is the height of the centroid. Okay. So in other words, just the vertical depth of wherever the centroid is. And this A right here is the area of the surface. Okay. And so that's one form of how to find the magnitude. Okay. And so the other way you can find the magnitude is you can just substitute in for specific weight. Because oftentimes in a problem, you're not given the specific weight, but you're given the density. But we also know that specific weight is nothing more than density times the gravity, okay, times hc times a. Okay. So this is kind of another form for this right here. Okay. Remember this row right here, this is density. Because it's it looks like a P, but there's no ponytail, right? So usually when I put a ponytail on the P, that means it's pressure, but this one has none, so it's just density. And here, this G is our good old gravity. Okay, and so I think kind of the, you know, most of these are pretty easy to figure out because you get the density and the gravity usually from the problem. The area is something that, you know, you'll have to read the problem in order to determine, because so you need to see whether you have a circular surface or a square surface or a rectangular surface. So I think that the one that kind of trips people up the most is this guy. Okay, and so you know, let's draw a figure just to kind of illustrate what that means. And so let's say that we have a surface right here, okay, and it's submerged in some water, just like that. And so on the surface, the way that you find the centroid is you simply go halfway down the surface. Okay. Okay. And then HC will simply just be the depth of that centroid. Okay. And so you have to be really careful here. So I think the place where a lot of people get confused is they confuse H for Y. Okay. And so whenever you see H is purely just a vertical distance from the surface of the fluid down to your surface. So this is just a purely vertical distance. Okay. And in this particular case, we're looking for the depth of the centroid itself. Okay. And so that's kind of what I mean by HC, right? And so the way that you find HC, a lot of times it's either given to you in the problem or it's something that you want to solve for. But if it's not, then you can basically just, you know, look at your surface, see where the centroid is, and find out the depth of that centroid, and that's going to be your HC. Okay. And so once you have HC, and once you compute area, you know, the magnitude is usually pretty straightforward. You just kind of plug those numbers in. Okay. Now let's talk about location. Okay. And so location, I think, is the part where people get really confused because it's, you know, first of all, it uses a different distance coordinate. Okay. Whereas in the previous example, or in the previous equation, we use H, which is just the depth of the centroid. Here we don't use H, but we use Y. Okay. And I'll show you kind of the difference in between them with this figure right here. Okay, so let's say that we have a surface down here. Okay. And so remember, H here is just the vertical depth of something, right? And so to get H, you just go vertically down. But Y is actually a distance here along the surface. Okay. So when you do compute Y for your location of the static force, you have to kind of tilt your coordinate axes in order so that the Y-axis aligns perfectly with your surface. Okay. Or not curved, sorry. Inclined. Okay. And so make sure you have this distinction between Y and H kind of clear in your head. Okay. And so now that we've defined Y and H, let's go write the formula for our location of the static force. Okay, so our location is YR, and this is equal to IXC all over YCA, okay, plus YC. Okay. And so let's define all the variables here. So first we have YC. So YC right here is the coordinate, the Y coordinate of the centroid. Okay. And so just like we did for the magnitude of the force, you know, the centroid of our surface is something that's going to be really important. Okay. But notice here that it's Y sub C, not H sub C. Okay. And so when you're computing this, make sure after you find the centroid, you find the distance from the surface of the water to that centroid, but you do it along the axis of the surface itself. Okay. And so this one, remember, you're not doing H sub C, but you're doing Y sub C. And so A, just like we did in the previous one, A is simply just the surface area, or the area of the surface that you're considering. And then this IXC right here, this is your moment of inertia. Okay. And so usually for the moment of inertia, you know, you're going to go off based on the shape of your surface, and then you're going to compute, you know, just plug into the appropriate formula for that. So you can either look this up in a table, or if it's something common like a rectangle or a circle, you know, you can just simply use that. Okay. Okay. And so, you know, I'll tell you guys kind of one exception to this, or not really an exception, but it's a special case. And you've seen this in the homework already, where if our surface here is vertical, okay, then if you have a vertical surface, the y-axis actually aligns with the vertical one. Okay. And so for vertical surfaces, you can substitute h in for y. Okay. And that kind of just simplifies your calculations a little bit, just because you're only solving things on one axis. Okay. All right. So those are basically just the two main formulas that you need. So oftentimes with these, you know, you're going to plug in those. At the very least, you're going to use these two formulas. Okay. And so one other thing that you might need for these problems that, you know, a usual kind of problem with these is to use them to compute moments about hinge. Okay. And so I don't think we explicitly cover this in the lecture, but I do want to cover it a little bit. Okay. You've used it up to this point, but I think it's worth it to kind of just review it really quickly. Okay. So a very common problem that you'll find in these, you know, in these kinds of problems is, you know, you have a gate that's going to be rotating about a hinge. And so oftentimes what you're going to need to compute is a balance of moments. Okay. Okay. And so just like you saw in the homework, you know, in the homework was a little bit unique because you had a moment that from one surface on the gate and a moment from the other surface of the gate. Okay. And so basically what we want to do is we want to sum up all the moments in the problem and set it equal to 0. Okay. So let's draw just kind of a simple case. So this is from the lecture notes. Okay. Okay. And so let's say that we have a hinged gate just like this. Okay. And you know, you can always determine the location of the hinge because it's going to be a circle. Okay. All right. And so in order to maintain static equilibrium, you know, the sum of all the moments here equals 0. So there's two forces acting on this hinge that's going to produce a moment. Okay. And so first of all, we have a force that's come from the static fluid. Okay. Okay. And so the static fluid is going to produce a moment. Okay? And so remember, the way that you compute moments is you simply just take the force and you multiply it by the distance to the hinge. Okay? And so in this case, the distance to the hinge here is this. So we'll call that L. Okay? And so the moment from the fluid here is just going to be the product of the force multiplied by the distance. Okay? And so that's the moment from the fluid. Okay? In order to balance this out, there also has to be a moment from the in this case, the stopper too. Okay? And so you have to look at your problem and you have to see, you know, oftentimes the other moment's going to come from something that's a bit unexpected. Okay? And so in the homework problem, the other moment actually came from another fluid that was on our surface because we had kind of an L8. Well, in this case, the restoring moment is coming from the this stopper right here. Okay? And so to balance it out, the stopper is going to apply a force right there. Okay? Okay. And then to compute this moment, you just do the same thing. So you just do the reaction force from the stopper. So I'll call that Fs, and then you multiply that by the distance to the hinge. Okay? So I'll call that Ls. Okay? Okay. And so we have F sub s times Ls, okay? And that's going to be our moment from the stopper. Okay? And then in order to apply this, sum of the moments is equal to 0. You just have to substitute these guys, or you have to set them equal to each other. Okay? Okay. And then from here, you know, it's depending on what kind of problem you're solving. You know, you can, you know, compute anything that you want. Okay. Okay. And so since this was kind of the most requested topic, I did want to do an example. Okay. One that you haven't seen yet. And just fair warning now, I'm kind of freestyling this, so I'm just looking in the book and seeing a problem. Okay. Okay. So in this example, let's say that we have a static fluid. Okay, it looks like this. And in the bottom here, we have an air tank. So let's say that we, you know, this is the bottom of our fluid. Okay. We have a tank that looks like this. Okay. Okay. And so inside the tank, we have air. Okay, so we'll call this P1, and we can assume the air pressure is constant. So even though the you know, this gate has some depth, you know, this air pressure here is going to be constant. Right. And so what's going to happen here is that because we have a hinge here at the gate, and we have a fluid, and we have an air pressure on the inside, this air is going to push on the gate just like that. Meanwhile, let me draw the geometry of the gate. And so we know that this angle here is going to be 30 degrees. Okay. Meanwhile, you know, the fact that we have water on the outside means that we're going to, you know, have a moment or have a force that's coming from the outside. And so let's say that we know this depth right here. So this depth is going to be 10 meters. Okay. And this lines up with the centroid of the gate. Okay. And so we know right away that this is going to be H sub C. Okay. And because we have the fluid on the outside, this is also going to exert a force. But this this force out here kind of respects the fact that, you know, we have a hydrostatic fluid. And so that force, the distributed force, just like we said before, is going to be higher at higher depths. Okay. Okay. So some other pieces of information. Our gate here is circular. Okay. And so the diameter of the gate is 2 meters. Okay. And so what we want to determine is, let's determine the pressure that has to be on the inside. The minimum air pressure on the inside that would be required to open the gate. Okay. Okay. So you can see obviously this is a hydrostatic force on a surface, and so let's go about solving it. Okay. And so just like we talked about before, the first thing that we have to do is we're going to take the fluid that's on the outside, which is water. Okay. And we'll assume the water has a density of 1,000 kilograms per meter cubed. Okay. And so first thing we're going to do is we're going to compute the magnitude and the location of the water pressure first. Okay. Okay, so first let's start with the magnitude. Okay, and so we know from our formula from before, magnitude is equal to rho g times the depth of the centroid, and then we're going to multiply by the area. Okay. All right. And so we're given the depth of the centroid here. So the depth of the centroid is 10 meters. And so let's just go ahead and start plugging in. Okay. Depth of the centroid here is 10 meters. Okay. And the area will be pi over 4 times the diameter squared. Okay. And so let me get my handy dandy calculator. Let's go ahead and plug all these in. And then what we get is a magnitude of 307,876 newtons. Okay, so that's our magnitude of the pressure force, and then now let's compute the location. Okay. Okay. And so remember our formula for the location is given by this guy. It's IXC divided by YCA plus YC. Okay. And so the area we've already computed in the previous part. And so in order to compute the location, we need to compute IXC and YC. Okay. Let's start with IXC because that one's a little bit simpler. Or IXC is the moment of inertia of a circle. Okay. And so the formula escaped me. So I'm going to look it up in a table online. Okay. In just a second, let me stall. Okay, and so remember the key here is this is the moment of inertia with respect to the centroid. Okay, and so the moment of inertia with respect to a centroid of the circle is going to be pi over 4 radius to the 4th. Okay, and so since our gate has a diameter of 2 meters, and so the radius is going to be 1, so this is going to be pi over 4 times 1 meter to the 4th. Okay, and this is simply just going to be pi over 4. Okay, so this is going to be 0.785 meters to the fourth. Okay, and so that's fine. And so the next thing that we need to do is the depth of the centroid. Okay, not the depth, the y-coordinate of the centroid. Okay, and so for this one, I think it's useful to draw a figure. Okay. Okay. And so we know from the figure that you know the incline of the gate is 30 degrees right here. Okay. And we know the depth of the centroid. So the depth of the centroid is 10 meters. Okay. And so what we want is this length right here. Okay. Okay. So you can do this in a couple different ways. But the way that I'm going to do it is by the parallel line theorem, I think. Since this angle is 30 degrees right here, we know that this angle is also 30 degrees. Okay. And if we go by our you know, sine, cosine, tangent rules of SOHCAHTOA, then we know that this length right here, or sine of 30 degrees, has to equal the opposite over the hypotenuse, so it's going to be 10 meters, divided by YC. And so to solve for YC, simply just going to be 10 meters divided by sine of 30. Okay. And then what we get is 20 meters. Okay. And so let's plug all that guy in, and just also remembering that A from the previous one, actually I don't know if we ever actually computed it, it's just be pi divided by 4 times 4. So it's going to be 3.14159 meters squared. Okay. So let's go ahead and plug all these guys into this formula. And then what we get is 20 divided by 3.4 times 0.79 plus 20. And we get oh, sorry. Let's see. I had a brain fart for a second. Okay, so 0.785 divided by 20 plus 20 times 3.14, okay, plus 20. Calculator's being weird. We get 20.0125 meters. Okay. So it's actually not that much farther. Okay. Okay. And so now that we have the magnitude and the location, let's draw these guys into the figure so that we can go ahead and solve this. Okay. Okay. So here's our gate. Actually, let me draw a little bit shallower because that's a bit more accurate. And so here on the outside, so we said that FR was our magnitude. So our magnitude was 307,876. Newtons. Okay. And then the location of this, all the way to the surface, was 20.125 meters. Okay. Right. And then opposing this moment is the air pressure from the inside. Okay. Okay. And since, you know, we said that the air pressure on the inside was constant, then the distance between this F air and the hinge is just going to be the radius. So it's just going to be 1 meter. Okay. Okay. And so what we need to do now first of all, we recognize that the force of the air is going to be the pressure of the air times the area. Okay. Remember, the pressure of the air is what we want to solve for. Okay. And so the last part of this problem is to compute. Now that we have this distance from the surface to here, is we need to compute the distance from from this force to the hinge. Okay. And so we want to get that L dimension right there. Okay. And so the way that we're going to do that is that we know that this distance right here between the surface and the centroid is 20. Okay. Right? Because we know that the y-coordinate of the centroid is 20 meters. Okay. And so the distance between this force and this is simply just going to be the difference in between the two. So we have YC, or we have YR minus YC. Okay. And so if we do YR minus YC, that gives us this little distance right here. Okay. And so this is going to be 0.0125 meters. Okay. Right. And then the distance from here to the hinge is simply going to be just 1 meter plus this, because the radius of our gate is 1 meter. Okay? And so L in this case will be the radius plus 0.0125. This will be 1.0125. Okay. All right. And so let's set these guys equal to each other. And so first we have the moment from the air, or from the water. Okay. So the moment that's resulting from the water is going to be 307,876. Okay. Newtons. Multiplied by the distance here. So we just computed that. So it would be 1.0125 meters. Okay. And this has to be equal to the moment that's resulting from the air. And so that's going to be the force of the air. So that's P air times the area. And so the area in this case is the same as we did before. So this is going to be 3.14 meters squared. Okay. And then multiplied by the distance, which is 1 meter. Okay. And so we can solve this equation for PA. Then what we get is what we get is 99,275.3 pascals. Okay. So that example was a good one because it kind of ran us through everything that we need to do for these kind of hydrostatic problems, which is compute the magnitude of the hydrostatic force, compute the location, use it to compute a moment, and then compare that to the opposing moment on the other side. Okay. Okay, so that's the review for the hydrostatic force on surfaces. So let's move on to the next topic, which is manometry. Okay. And so manometry is kind of that was kind of the first application that we saw for our hydrostatics. Okay. And so this took place kind of just after we derived that equation for how does pressure vary in a static fluid. Okay. And so the idea with manometry is to use these pressure variations in order to measure pressure differences. Okay. And so, it gets this name because the original device that was used to measure these pressure differences was called a manometer. Okay. And so there's kind of one big equation and one kind of hidden equation that that you can use to solve these kinds of problems. And so the first one that we'll go over, we saw this earlier in the review session, where if you have a tank of water, okay, and you consider two different locations, and the height in between them, h, okay? What we can do is we can compute the pressure difference between these two, okay? And remember, the convention that we had was that we usually put the higher location first. So in this case, P1 is up top, and we do P2 on the bottom. Okay. If you want to swap this up, that's fine. It's just you have to change the sign of the other side. Okay. Right. And so the pressure difference in between these two will just be minus H, which is their height difference, times rho times G. Okay. And so basically, whenever you're moving vertically in a static fluid, you have to account for the pressure differences, and the way that you do that is with this equation. Okay. And so the other kind of kind of implicit equation that you probably already using is this one right here. Okay. And so say that you have 2 points, they're at the same depth. Okay. And so when you have 2 locations at the same depth like this, then we say that their pressures are equal. Okay. Okay. All right. And so these are kind of the building blocks for for how to do manometry equations. So manometry questions. So again, with the same that we had with our hydrostatics, there's not many equations here. It's more just how you apply it. So so with these kinds of things, it's the only way that you kind of get better at it is by exposing yourself to more practice. So in addition to the homework, see what examples there are in the book, and see what additional homework problems or problems you can do in the back, and then use that to kind of give yourself some more practice. Okay, and so for this one, what I thought I would do, because I think it's a pretty good problem, is to go over the homework problem for this. Okay, and so the homework problem, I think this is problem 2, homework 2. Okay, and so problem 2, homework 2, problem 2 of homework 2. This is a very classic example of what's called a differential manometer. Okay, so it looks something like this. And so let's say that we have a different fluid on the inside here. Okay. And I want to touch on this too, because I noticed it a lot in the last homework, that when I say gauge fluid, what I mean by gauge fluid is the fluid that you actually use in the manometer here. So the gauge fluid here would be the purple one. Okay. And so what makes a good gauge fluid is actually a fluid with a very high density. Okay. And the reason for this is that, if you go back to our previous page, okay, we know that the pressure differences depend on the height, and they also depend on the density. Okay? And so if you have a given fixed pressure difference, if you have a fluid with a very low density, okay, if you have a fluid with a low density, the way that you get a you measure a big pressure difference is that your H has to be massive. Okay. Okay. And sent by the same token. So if you have a high density, so if you have a high density, then in order for you to compute that same pressure difference, you only need a modest, change in height. Okay? And so the reason, we would want to have a fluid with a high density is because oftentimes these devices are space compact, so you don't want them to take up too much space. And so if you have a liquid with a very low density like helium, in order to measure pressure differences, you have to have a very, very tall device, which oftentimes is just not that practical. So if you use a fluid like liquid mercury, which has a very high density, then you only need just a small device in order to measure biggest pressure differences. Okay, so let's get back to the problem. And so in this problem, we had 2 locations, A and B, and we had flow that's going through there. Okay. And what we were interested in solving for is what are the pressure differences in between A and B. So we have PA minus PB. Okay. Okay. And so in addition to this, we have some heights. And so we know that this height right here, this is H1. Okay. We know that this height right here, let me erase this guy a little bit. We know that this height right here is H2. Okay. And so what this problem wants us to do is to use the manometer and to get an expression for PA minus PB. So I know in the homework that I plugged in numbers for this, but I think it's good practice to run through these kinds of problems without the numbers, just so that you get some practice doing that. Okay. Okay, so let's start doing this. So the way that I've been recommending people to do these kinds of problems is to give yourself some auxiliary points, because if you just kind of look at this problem like this, you know, there's kind of a lot going on. So the way that I usually solve these is I kind of just work my way around the manometer. And you know, when I say work my way around the manometer, I mean that you can physically go from one point to the other point. So we can either go from point A to point B, or from point B to point A. Okay. But how you move around the manometer is really important. So, you know, let's say that the only types of moves that we can make are either purely vertical moves and purely horizontal moves. Okay. And so by doing this, you know, we'll be able to use our two equations right here. So for a vertical move, we'll use the equation up top, and then for a horizontal move, we'll use the equation on the bottom. Okay. And so let's go about start by adding points. Okay. And so let's go from point A to up here. So this is purely vertical move, and we'll call this point 1. Okay. Next, let's go horizontally across to the next two, and then we'll call that point 2. Next, we'll go vertically or horizontally across to the gauge fluids, and that'll be point 3. Next, we'll go vertically up onto the top of the gauge fluid, so that's going to be point 4. And then we'll go horizontally across to point 5, and then from there we can go vertically down to B. Okay. And so let's traverse through all the points, and then along the way we'll write the expressions for the pressure that we need to do. Okay. Okay. So first, let's go from point A to point 1. Okay. And so this is a vertical move. So for a vertical move, we're going to use our pressure difference formula. Okay. And so for this particular case, it'll be P1 minus PA, because point 1 is the higher point and A is the lower point. Okay. And this can be equal to the minus the height difference. So we have H1 times the density. And so let's say that the density of the fluid here is ρ1 times gravity. Okay. Right. All right, so next we're going to go horizontally across, and so we're going to go from point 1 to point 2. And we know when we make a horizontal move, we just do P1 and P2. Okay, and those two are going to be equal. And then next we're going to go horizontally across again from point 2 to point 3. Okay, and then we're going to set those pressures equal to each other. So P2 is equal to P3. Okay. Okay, and so let's move on to the next page. Okay, and so next we're going to go from 3 to 4, and so 3 to 4 is a vertical move. Okay, and so let's do the higher point minus the lower point. So we have P4 minus P3 is equal to minus H2 ρ2. ρ2 is the density of the gauge fluid times G. Next, we're going to go from 0.4 to 0.5. So this is a horizontal move. So we can say that P4 is equal to P5. And then finally, we'll go from 0.5 down to point B, which is a vertical move. So we're going to have P5 minus PB is equal to minus. And so in this case, it's we drop an entire, H1 plus H2. So we're going to do H1 plus H2 times rho 1 G, because this move takes place in the first fluid, which is rho 1. Okay. And so these are basically this is basically the setup for all these problems. And so now what we have to do is we have to manipulate these equations and substitute in or make substitutions until we get PA minus PB. Okay. Okay, so let's start that process. Okay. So let's start with our first equation right here, and note that we have P1 right here. Okay. And so first, let's go about eliminating P1. And so to eliminate P1, we can use this formula right here. So we can plug P2 in for that. Okay. And so we have P2 minus PA is equal to minus H1 rho 1G. Okay. And then now we need to eliminate P2. And the way we can eliminate P2 is using this formula right here. Okay. And so from that, we can say that we have P3 minus PA is equal to minus H1 rho 1G. Okay. So let's go ahead and write that down. Okay. And so now we need to eliminate P3. Okay. And so the way that we're going to do that is we're going to use this equation up here. Okay. And so if we solve that equation for P3, then we get P3 is equal to P4 plus H2 rho 2 G. Okay. And so let's substitute this guy into this equation right here. Okay. To eliminate P3, so we get P4 plus H2 rho 2 G, okay, minus PA is equal to H1 rho 1 G. Okay. And so now we need to eliminate P4. And so from here, we can see that P4 is equal to P5. And so what we can do is that in this equation right here, we can just substitute in P5. Okay. And then finally, we're going to use this last equation to eliminate P5. So if we solve this equation for P5, what we get is P5 is equal to minus H1 plus H2 rho 1 G plus PB. Okay. And so let's substitute that in for that. And we get minus H1 plus H2 rho 1 G plus PB plus H2 rho 2 G minus PA is equal to minus H1 rho 1 G. Okay. And so that's the final expression that we have right there. Okay. And so you can simplify this a little bit. You can see that this H1 minus H1 rho 1 G is going to cross out with this guy, and then you get a much simpler expression for this. Okay. And so we can solve for PA minus PB. Okay. And then what we get is PA minus PB is equal to, so we'll put PA over there. This PB is not part of this. Minus PB is equal to H2G rho 2 minus rho 1. Okay. And that's the expression from that. So with these manometry problems, you know, the best way to go about these is do it really systematically, step by step. And then from there, you end up with, you know, expression at the end. So draw in as many auxiliary, as many extra points as you need, because I think these problems are easiest to tackle when you're going just vertically and horizontally. Okay. Okay. So that's everything with manometry. So again, manometry, there's, you know, really not much to it. It's just you just have to do a few extra practice problems in order for you to kind of get the hang of it. Okay? And so for the last, you know, 15 minutes, I do want to touch on Bernoulli. Okay. And so Bernoulli equation, you know, this was just our most recent topic, and it's kind of our first foray into fluid dynamics. Okay. And so in contrast to everything that we covered before this, now our fluids are going to be moving most of the time. Okay. And when you have a moving fluid, you know that it has velocity. Okay. And so the kind of the pure form of the Bernoulli equation looks like this. And so if you take the pressure, so that's P with the ponytail, divided by the density, and then to that you add the kinetic energy term, so you have 1/2 U squared, okay, plus GZ. Okay. This has to be constant in a fluid. Okay? And so this sum of these terms always has to be constant. But, you know, these come with a caveat. Okay? And so we have to make some assumptions here. And so the assumptions that we make, there's 4 of them. Okay? So there's 4 key assumptions. So first of all, we assume that the flow is incompressible. To me, incompressible always sounded like the song Beyonce never wrote. You're incompressible. I'm glad none of you are here because, you know, you'd all be laughing right now. Okay, so the second assumption here is steady. Okay, so remember steady, all that means is that the fluid's not accelerating or decelerating. Right, so the third assumption is inviscid. And so all inviscid means is that we can ignore viscosity. And the fourth assumption is that we apply this along a streamline. And so all that last one really means that you apply it in the direction of the flow. So you have to apply it along the flow, right? And so this is the Bernoulli equation right here. But a lot of times we don't use it strictly in this form because the way that we usually use Bernoulli is we use it to compare between 2 different locations. Okay. And so what that means is, say that we have a moving fluid like this, okay? And then we have some location 1 upstream and location 2 downstream. Okay? And so what we can do is we can write out the Bernoulli sum, you know, the sum of all 3 terms for both of those locations. So let's do that for point 1 first. Okay. And then we're going to write that out for the same thing for point number 2. Okay. And since, you know, if we can apply all 4 of our assumptions here, where the flow is incompressible, steady, inviscid, and, you know, we can see we apply along streamline, these 2 guys have to be equal to each other. Okay. And so a lot of times the way that you're going to solve these problems is that, you know, say that you want to solve for something like the pressure at point 2. Okay? So this is just a theoretical example. Okay? And so to solve for the pressure at point 2, all you have to do here is to plug in all the values for all the other stuff. Okay? And so usually the way that this goes is that you'll know all the conditions upstream, so you'll know all the pressures and the velocities and the height at point 1. Okay? And you'll usually know most of the other stuff at the other stuff. Okay? Okay? And so you just plug in everything, solve for that one pressure, and then you're good to go. Okay. Okay. And so kind of the other big thing that you need to know for Bernoulli, just in kind of the short time that I have left, is conservation of mass. Okay. And so what conservation of mass says that if you're in a confined flow, or in other words, the fluid only has one direction to go. So in a confined flow, what you can assume is that the mass flow rate is always going to be constant. Okay. And so the mass flow rate, we give it the symbol m dot, is equal to rho times A times U. Okay. And so the other thing that's useful is that most of the time, if we assume that our fluid is incompressible, that we know that the density is constant, then the other thing that we can solve for is Q, which is A times U, and Q here is the volumetric flow rate. Okay. And so the way that you use this in practice is kind of the same way that you apply Bernoulli. And so you take two locations in the flow. Okay. So let's say that we have something like this. Okay. We have just a simple diffuser. Okay. And so we have two locations here, point 1 and point 2. If we assume that the mass flow rate is constant here, then we can say that the mass flow rate at location 1, so rho, times the area at 1 times the velocity at 1. Okay. This has to equal to the density, the area at point 2, and the velocity at point 2. Okay. If we cross out the densities here because they're the same, then we get A1 U1 is equal to A2 U2. And so it's the same kind of idea. So the theme of Bernoulli is that you always kind of take two locations in your flow, and then you compare the quantities against each other. So not only does the Bernoulli sum have to be constant, but the mass flow rate also has to be constant. Okay. Okay. And so this leads to a lot of really interesting phenomena. So I don't think I have time for a full example, but I do want to kind of mention a few extra tidbits. Okay. So the first thing is stagnation, right? And so stagnation, whenever you hear that term, all that means is that the velocity is 0. Okay. And so I think the example that we introduced it with was, say that we have a building and we have air that's hitting the building. Okay. Right at the location when the air strikes the building kind of straight on, this is what's called a stagnation point. And so a stagnation point is nothing more than just a location where the velocity is 0. Okay? And so in particular, because stagnation points are so important, because the velocity is minimum there, the stagnation pressures, which are the pressures at the stagnation points, these will be the highest pressures, usually one of the highest pressures in the flow. Okay. All right. And so that kind of brings us to kind of another important relationship, which is the relationship between velocity and pressure. Okay. And so typically what happens is that if you have a higher velocity in your flow, that means your pressure is going to be small. Okay. And then the opposite is true too. So for locations where you have a small velocity or low velocity, okay, these are going to have higher pressures. Okay. And so there's that inverse relationship that that you will find usually in these kinds of problems. Okay. Okay. All right, so that's kind of the basics of Bernoulli right there. So, for most problems, what you're going to apply is, first of all, you're going to apply conservation of mass, and then you're going to apply the Bernoulli. And then from that, you can start to solve for some of these fluid dynamics quantities, okay? But I would say, that's the Bernoulli equation itself is really important. But, I want you to always remember what these 4 assumptions are right here, okay? Because with the 4 assumptions, because, in order to apply Bernoulli, this kind of relatively simple formula, we need to have all 4 of these conditions satisfied. So if they're not going to be satisfied, then you can't apply Bernoulli, and you'll have to use a method that we're going to go over the next couple of weeks. Okay. All right. So I think that's it for this review session. So that's all I got time for. So hopefully you guys found this helpful, and if so, I can definitely do these for the second midterm and for the final exam as well. Okay. And I'm sorry, that I couldn't do this in the class. Normally I like to do that, but I am falling a little bit behind in my lectures. So I didn't want to just skip it outright. So I wanted to make sure that you guys got some review. And so with this, together with the study guide, hopefully will be great tools for you to study for the exam. Right? And so as always, if you have any questions about anything that we covered in this review session or just anything in general, you can always send me an email. You can direct message me on Discord. You can do any of those things, and I'm always happy to answer. With that, I guess I'll sign off. Best of luck on the midterm.